Okay, carrying on in 1.3 here, example 2, just looking at some different ways that geometric sequences show up in reality. And it is, I don't want to say this because it's such a bold thing to say, but I'm going to say it anyway. Geometric sequences are probably more common in nature than arithmetic sequences. And part of the reason for that is really particularly, population growth. But this particular example isn't that. So let me kind of stop getting off topic. It says that we use a photocopier to create enlargements or reductions. It says the actual length of the photograph is 25 centimeters, and then the smallest size is 67%. Now, what that means is that the photocopier can make this image 67% of what it is. And right off the bat, this is my particular pet peeve, that 67% corresponds with 0.67. And that really means that if I want to find 67% of something, I could multiply it by 67 and then divide by 100. That's what percent is. Or I could just multiply it by 0.67. And the reason why that's so important is this becomes our common ratio. Now, this question has kind of a classic problem where it's very common to start off with 25. And then my next term would be 25 times 0.67. But what's really important is that 25 is the original. And then this 25 times 0.67 is after one reduction. And the reason why I push this concept so much is that if we want to represent this as a geometric sequence, it is a bit of a bummer or a bit misleading to say that 25 is term 1 because we haven't done a reduction yet. And you can, don't get me wrong, if you make 25 term 1, then 5 reductions will be the 6th term. Whereas if I make this right here, 25 times 0.67 term 1, then term 5 is after the 5th reduction. And I think that's a really, really big benefit because it makes it much simpler to look at this. Now, I would like to do the other terms here. This would be 25 times 0.67 squared because I would multiply this red term by the common ratio, which is 0.67. And that's important that to go forward in this sequence, we have to multiply by the common ratio. And the way that I've set it up now, this 25 times 0.67 squared is the second reduction, but it's also going to be term 2. So what I'm going to do is instead of using that term 5, we're going to cross it out. We needed it because we needed to know what the original was, but now I can say that one reduction is term 1, 2 reductions is term 2, 3 reductions, 4 reductions, and so on. But what we're going to say, and it's a little bit of an ugly number, but we're going to leave it in exact form, is the first term then is going to be 25 times 0.67, and my common ratio is going to be 0.67. That allows me to come up with the general term. I'll put the formula right here. The general term is term 1 times r to the power of n minus 1. For our question, Tn, the general term specific to this question, is going to be, and I'm going to use a couple different brackets here to try to make it really clear. Term 1 is this entire square bracket. The common ratio is 0.67, and that is to the power of n minus 1. I'm just going to draw an arrow here that this entire square bracket is term 1, and then the common ratio snuck inside that round bracket there. Now, there is certainly some math cleanup that we can do here. A lot of students don't like doing this, but I think it's really important to build these kind of exponential skills. I'm going to write this just a little bit different and say that Tn is 25 times 0.67 to the power of 1 times 0.67 to the power of n minus 1. And that's exactly what I had above, right? Just splitting that square bracket into 2 different factors. The reason why that's so important is that what I'm underlining here has the same base. So I can write Tn as 25 times the common base of 0.67. And then what I'm going to do is I'm going to take their exponents and I'm going to add them. So when I look at that exponent though, what's n minus 1 plus 1? Well, it's just n. So Tn is going to be 25 times 0.67 to the power of n. And that is much easier to work with than this form right here that I put an asterisk. Now, don't get me wrong, mathematically they're equivalent. They'll give you exactly the same thing as you use different ends along the way, but I think we probably all agree that what I put in that black box at the bottom is going to be a little bit easier to use, because what we need to do now is I'm going to say that 5 reductions is going to be term 5. Now remember, the number on the T there is the subscript. It just tells me what I'm putting in for n. So if I use these 2 things with each other, I'm going to be able to say that term 5, or the 5th term, the 5th reduction, is 25 times 0.67 to the power of 5. And I really want to push that concept that what I underlined twice is a subscript, what I circled is a variable. And it's so important to understand the difference between them. This little 5 on the term is just there to know that we're talking about term 5. Because otherwise, I mean, if I just wrote t, which term is it? Is that T1, T2, T3? We don't know. But now I know that this is the 5th term in the geometric sequence. And at this point, we certainly need to grab our calculator. I'll give you what that value is just to make sure that we're putting in it correctly. 0.67 to the power of 5 is a little bit gnarly. It's 0.1350125,107. When I multiply that by 25, I get, after 5 reductions, this photograph is going to be 3.3753127. Just putting all those decimals so you can check your work on the calculator. And sorry, I have to scroll up. It asks, express your answer to the nearest 1/10 of a centimeter. So we're going to say 3.4 centimeters. All right, not too bad of a question. I mean, it definitely gets a little bit trickier when we have to try to figure out what n is. This is usually, or this is the more direct approach where we're trying to find out a specific term in a geometric sequence.